So suppose we didn't have calculators, the horror, right? And say you wanted to know the value of a function that you can't easily evaluate by hand, like sine, right? We can only really evaluate the sine function at our unit circle values. And other than that, we don't know exact answers, off the top of our heads at least. So we might need to approximate it. So say, for instance, we want to approximate the sine of 1. We're going to come back to this a little bit. Right, we have a variety of ways of calculus to do that. We can find the tangent line at a point close to that and use a tangent line approximation, right? So 1 is pretty close to pi over 3. So maybe we write the tangent line at pi over 3 and then plug in 1 to that instead, see what we get. We can do Euler's method, and the more steps we do, the smaller steps we take, the more accurate, the closer we're going to get, right? And we can also use a Taylor polynomial. Right, so the higher degree Taylor polynomial we do, the more accurate, the closer we will be to sine of 1 as well. And using a Taylor polynomial is super nice because then you're just plugging into a polynomial. So you're just dealing with x's, there's no pi's or anything like that. You don't have to take a ton of, steps or anything like that. Just find the polynomial, plug it in, especially since we know what the Taylor polynomial is for sine if it's centered around 0. So if we're approximating something, we might want to know how close is that approximation, right? How much error is there in between what we're actually wanting to find and what our prediction says it's going to be, our approximation. So if we let t sub n of x be the nth degree Taylor polynomial, right? So our n here is just matching whatever degree Taylor polynomial we have. And we're centering that at some x equaling c value, so that's some center for this function. And we're trying to use that to approximate a function value at a, f of a. And that x equaling a value's got to be kind of close to x equaling c, right? If you're going to center your polynomial at x equaling 2, you probably don't want to use it to predict x equaling 50, right? Too far away. So when we're doing this, right, our predicted value would be the value that we get out of our Taylor polynomial, right? Our nth degree Taylor polynomial, we would plug in a, that would be our predicted value, our approximation. The actual value is f of a, right? That's what we actually want to know. That's the accurate value. Our error is the difference between those two. So our error is the difference between our predicted and the actual, right? The absolute value, because error is just how far away are you. It doesn't tell you which direction necessarily you're in. So in our case, we have the absolute value of t sub n of a minus f of a. So just like alternating series has a remainder to it, and we can figure out what the maximum error is, so do Taylor polynomials. And this is where something called the Lagrange error bound comes into play. So the Lagrange error bound, it's also just called the Lagrange form of the remainder or Taylor's theorem. All three names mean the same thing. Right? Taylor's theorem because it's about Taylor polynomials. So this is going to look super complex. We're going to read through the actual math of it, and then we're going to explain what all of this means. So the function f is differentiable through order n plus 1, which means that you can take n plus 1 derivatives of it. So it might not have an infinite number of derivatives, but you can take a derivative so far to create your Taylor polynomial. And it has those derivatives that are in an interval containing x equaling c. Right, so c is your center point. For every x value in that interval that is not c, so x equaling a, there exists another number, z, that's between a and c, such that the Taylor polynomial, this is just our Taylor polynomial, setup. Right, so if we look at this equation, we have f of a, so this is the actual value of f of a. That's going to equal the Taylor series. And these are all typos. These should all be a's plus some remainder. Right, so our Taylor polynomial at x equaling a is this part here, right? That's our approximation, our prediction, plus the remainder is going to equal the actual value. And to find this remainder, so the remainder r sub n, so n is just matching the degree of the Taylor polynomial, is given by this crazy looking absolute value. So it's equal to the absolute value of the nth plus 1 derivative of z. So that's what this is here, right? This is the nth plus 1 derivative at z divided over n plus 1 factorial times a minus c to the n plus 1 power, right? So where a is the number you're trying to find the value at, c is the center of your Taylor polynomial. That's a lot. It looks super crazy, and it actually isn't as hard as it makes it look. So we can't always figure out what this z value is. So knowing what z is kind of impossible. So what we do instead to play it safe is we're going to pick an upper bound or a maximum value that the n plus 1 derivative meets on that interval. And so we're going to go through a few examples to show you how that works. So we're really going to replace this right here. Right, this is just going to become the max value of f to the n plus 1 of x, the nth plus 1 derivative of x. Right, you're going to see what I mean. So let's look at example 1. We're going to let f be a function with 5 derivatives on the interval from 2 to 3. We're going to assume that the fifth derivative of x, the absolute value of the fifth derivative of x, is less than 0.3 for all x in that interval. And that we are using a fourth degree Taylor polynomial, so we are using t sub 4 of x, centered at c equaling 2, right? So here's our center point, and we're being used to approximate f of 3, right? So a is equal to 3. That's the value we're trying to actually find. So how accurate is this approximation? Meaning how much error could there possibly be in using a fourth degree Taylor polynomial to approximate this function value? We're going to give our decimals to 4 decimals for this answer, which means I should probably figure out where my calculator is. Ah, there it is. Okay. So what this means is, so our error, so we're using a fourth degree Taylor polynomial. So r sub 4 of a, so that's 3, has to be less than, actually, we'll set it up this way first. It's going to be exactly equal to the absolute value of the fifth derivative, and that's because if we're doing a fourth degree Taylor polynomial, n plus 1 is 5, evaluated at some z value over 5 factorial times a minus c, so I'm going to get 3 minus 2 to the fifth power. Now, we don't know what the fifth derivative of z is equal to, so we know that has to be less than or equal to. In this case, we can actually say strictly less than. And now they give us a maximum value of the derivative, right? This right here is the max value of the fifth derivative. So we're going to plug that number in. So we're going to say that has to be less than 0.3 over 5 factorial times 1 to the fifth. All right, so if we grab our calculator, we're going to do 0.3 divided by 5 factorial times 1, right? So that doesn't even matter. So we're going to get an error of 0.0025. So that's the maximum error in our approximation. It's pretty close to the actual value. So now suppose in part B that we use our fourth degree Taylor polynomial and approximate 3 to be 1.763. So this is our prediction. We want to find an interval in which f of 3 must actually reside, the actual value of f of 3. Right? So the interval is always going to be, so f of 3 has to be within that error window of our prediction. So f of 3 has to be an element of, so that's this little fancy symbol, that means element of, so that means inside the interval of, or is contained within. We're going to take our prediction and subtract our error. And we're going to take our prediction and add our error. So that means, and that should be in bracket. So that means that f of 3 is in the interval 1.7605 to, I'm going to switch my minus to a plus, 1.7655. Right, so really not that wide of a window that it has to be in between. So if you were trying to get a good approximation, this isn't a bad one, right? The error is pretty small. So let's look at an example where they don't tell you the maximum value of the derivative and you have to figure it out yourself. So we're going to use a 5th degree Maclaurin polynomial to approximate sine of 1, and then we're going to find the maximum amount of error, so the Lagrange error bound for that. So the first thing we need to do is write down our 5th degree Maclaurin polynomial. So for sine of x, right, that's equal to x minus x cubed over 5 factorial, x over 3 factorial. Okay, just getting ahead of myself there, right, because that's plus x to the 5th over 5 factorial. This is why you don't do calculus when you're super tired. Okay, so sine of 1, to approximate that, right, that's about m5 of 1. So if I plug in 1, I get 1 minus 1, 3 factorial. 3 times 2 times 1 is 6, right? Plus 1 over 5 factorial is going to be 120, right? So 1 minus 5 6 is, 1 minus 1 6 is 5 6, right? Plus 1 over 120. That would equal, okay, that's 101 over 120, right? Just multiplying the top fraction, the first fraction, by 20. Right, so that's our approximation, and now we want to know our error, right, and that's our Lagrange error bound. So our error amount, r sub 5, of a, which is 1, because that's what we're approximating, that's going to be equal to the absolute value of our 6th derivative, because that's n plus 1, right, 5 plus 1, of some z value over 6 factorial times our a value 1 minus, it's Maclaurin, so we're centered at 0, raised to the 6th power. And so now that's going to have to be less than or equal to, and now we need to know the maximum value, right? So we need the max value of the 6th derivative of our function. So we're going to have to do some derivatives. So we've got our function starts as sine, right? So first derivative is going to be cosine, right, and we just keep going. All right, so my 4th derivative is then going to be positive sine. 5th derivative is cosine. And then finally, the 6th derivative is negative sine. So we want the maximum value of that function. Well, negative sine of x is always less than or equal to 1. Right? Right, the biggest value of sine or negative sine is 1. So we're going to plug 1 in for our top for the max error of sine of x, negative sine of x, right? And then 6 factorial, that's 6 times 5 factorial. 5 factorial was 120, so 6 factorial is 6 times 120, so that's 720. Oops. My hand switched my font color. Okay, 720, and then 1 minus 0 to the 6th is just 1, so we don't have to really worry about that. So we have 1 over 6 factorial, which is 1 over 720, so pretty small. If you were to use a calculator, you would figure out that that is less than 2 100ths off. It's 0.00138 on your calculator if you were to be having a calculator for this question. So the maximum amount of error is 1 over 720. So we're going to do one more problem, and it's again going to be one where you don't know, you aren't given the maximum value, you have to figure it out. So now we're going to use a 4th degree Maclaurin polynomial for e to the x to approximate the square root of e. And then we're going to find the error bound for the maximum error. All right, so same sort of problem. We're going to start with the Maclaurin series. So we have m4 of x for 4th degree Maclaurin polynomial, and e to the x, right, that's not too bad. We've got 1 plus x squared over 2 factorial, plus x cubed over 3 factorial, plus x to the 4th over 4 factorial. Actually, I said no calculator. We're going to need a calculator. We're going to use one. Erase that. Right, so the square root of e, right, is just equal to e to the 1/2. And that's going to be approximately my Maclaurin polynomial at 1/2. So I'm going to go over to my calculator, which you guys can't see on my screen. So I'm just going to type it in. So 1 plus 1/2 plus 0.5 over 2 factorial. So 2 factorial is 2 plus 0.5 over 3 factorial is 6. Right, you can, of course, type in the factorial symbols. 4 factorial is 24. And then 1, 2, 3, 4, 5 terms. 1, 2, 3, 4, 5 terms typed in. I'm going to get that this is about 1.854. Okay, so then let's figure out our maximum error for the Lagrange error bound. So our error, right, we're doing r sub 4 of 1/2, because that's the value we plugged in for x. That's going to equal the absolute value of the fifth derivative of some z value over 5 factorial times 1/2 minus 0 to the 5th power. So that has to be less than or equal to. Now we have to do our maximum value. So we need to know the max value of the fifth derivative of x. Now, since this is e to the x, right, we know that the fifth derivative is still going to be e to the x. So now, let's talk about what this last part of the problem means. It tells us that the absolute value of x has to be less than or equal to 2.5. So we need to figure out kind of a window to give us a safe bet on what the maximum value could be. We don't just want to like willy-nilly pick a value. So we want to find the max value when x, the absolute value of x is less than 1/2. So that's really telling us to find the error on right. It's kind of looking like 0 to 1, right? So we know that e to the x is an increasing function. So we know that e to the 1/2 is going to be less than e. Right? So our fifth derivative of e to the x on that interval is going to be e, but we want to just pick a nice number to plug in. So we know that e is less than 3, so a nice easy upper bound for this would be 3. That's a safe bet there. So we're going to plug in 3. Right, because remember, the Lagrange error bound would have been done by hand, so you wouldn't have been able to plug in e for this function, which is why we're picking 3 instead of e for our calculators. So then if we go to our calculators and type in, let's see, we got 3 over 5 factorial, so that's 120, times 1/2 raised to the 5th power, we have an error, a maximum error of 7.813 times 10 to the negative 4th. So that's a really small error, right? So those are just a couple of examples of how to use the Lagrange error bound, and it's really just focusing on, remember, you have to do the n+1 derivative. So if you have a 6th-degree Taylor polynomial, you have to use the 7th derivative. You're going to divide that by 7 factorial, and then instead of using like the z value, because we don't know what that is unless they tell us, we're going to just be figuring out what the maximum value of that derivative is and plugging that into our equation.